Now that we know that the difference in mass of the separated nucleons and the nucleus is known as the mass defect, and we know the mass defect is related to the binding energy through this mass energy equivalence here, we can go further to unpack this equation actually. So we say that mass and energy are equivalent to each other. So we can say that even though these are the mass of the constituent particles, we can convert it to be the energy of the constituent particles. And this is the mass of the nucleus, but we just say it as the energy of the nucleus. And of course, this energy involved here, for this transition to happen, we call it as the binding energy. If you rearrange this equation, we'll get that binding energy as our subject, and it can be the difference in the energy of the constituent particles minus the energy of the nucleus. Okay, so you can think of this equation here comes into place by taking this equation here multiplied by c squared on both sides. So the mass defect multiplied by c squared, you get the binding energy. So if you get the mass of separated nucleons multiplied by c squared, you get the rest mass energy of the separated nucleons, or the rest mass energy of the constituent particles. If you get the mass of nucleus multiplied by c squared, you get the rest mass energy of the nucleus itself. So that allows us to form this equation where you get the binding energy to be equal to the energy of the constituent particles minus the energy of the nucleus. Of course, if you unpack it back into mc squared, you get this equation over here. The binding energy, retain it as binding energy, but you unpack the energy of the constituent particles to be mc squared, where the m being the mass of the constituent particles. You can unpack the energy of the nucleus here, the rest mass energy of the nucleus, to be mc squared, where the mass being the mass of the nucleus. And if you factorize out the c squared, you can see that what's in the bracket over here is actually our mass defect. And that allows us to come back to the same equation, where the binding energy is equal to the mass defect multiplied by c squared. Okay, so I'm just spinning things around to let you see how everything are related to each other. Okay, so we are going to break this equation further. So this is the equation that we have just now, but I'm going to unpack this mass of constituent particles over here. So we know that constituent particles are made up of protons and neutrons. So if we know how many protons we have, how many neutrons we have, we can just add them up, their masses, their individual masses, then we can get the mass of constituent particles. So mass of proton, it's a defined value. We can find it from the constant sheet for our syllabus. Mass of neutron is also a very specific value, which you can find from our constant sheet over here. So if you are able to know for that nucleus how many protons there are, how many neutrons there are, we can get the mass of constituent particles. So Z here is the proton number, or you can say as the atomic number. So how many protons are there is represented by this value here. So how many protons are there multiplied by the mass of proton, you are able to get how much is the proton, how much does the protons contribute to the mass of constituent particles. Okay, if you have the number of neutrons multiplied by the mass of neutrons, you get how much mass does the neutrons contribute to the mass of constituent particles. So if you add them up, you get the total mass of all the individual separated nucleons that we need to form the nucleus. Okay, so this bracket here is the mass of constituent particles, so minus the mass of a nucleus, which we retain it as the same thing. Okay, so this equation here allows us to determine the binding energy, where we can find the mass defect first by calculating this mass of constituent particles minus the mass of nucleus. So once you get this mass defect multiplied by c squared, you are able to get the binding energy. Okay, this equation here can also be changed to become, we can unpack the mass of a nucleus to be the mass of atom minus the Z multiplied by mass of electron. Z here is the mass of proton, not mass of proton. Z here is the proton number, sorry. Proton number is the number of protons, but we know that for any atoms, when they are in their original state, the number of protons is the same as the number of electrons. So this Z here, you should also think of it as the number of electrons. So if you get the number of electrons multiplied by the mass of electrons, you are able to get for that particular atom how much is the mass of electrons, okay, surrounding the nucleus. So if you get the mass of atom, which include the electrons, minus the mass of electrons, you are only left with the mass of the nucleus itself. Okay, so you are actually eliminating the electrons mass from the overall mass of the atom, because atom includes the nucleus and also its surrounding electron. So this process here eliminates the surrounding electron, so we are only left with the nucleus over here. Okay, so both of these equations can be applied. If you're focusing on what's in the bracket over here, what's in the bracket here is the mass defect. So if the question asks for mass defect, you can calculate using what's in the bracket over here. But you can also calculate using what's in the bracket over here to get mass defect. But if you want to determine the binding energy, just multiply it by c squared, then you are able to get the binding energy. Okay, so there are other ways to represent this equation as well, which I'm going to unpack here. So this is the equation that we have just now. Okay, but I'm going to unpack it by saying that I'm going to add the mass of electron, the total mass of electrons, and minus also the total mass of electrons of this particular atom. Okay, so if I add and minus the same thing, technically they should cancel out, then I'll get back the equation up there. So what I'm trying to say here is I'm not disturbing the equation in any sense. It is still the same equation, but I'm adding and minusing the same thing at the back. Why do I do it like this? It's because I want to rearrange the equation into this form over here. If I rearrange the equation into this form over here, you can see that the mass of proton over here, adding on with the mass of electrons over here, what am I doing here is I'm having one proton and one electron is actually equivalent to one hydrogen atom. So I can rearrange protons and electrons to be grouped together. So since one proton and one electron is one hydrogen atom, you can take this bracket here to be, we have the Z number of hydrogen atom. Okay, Z number of hydrogen atom. The mass of neutron remains the same. This is the mass of neutrons that we can obtain. But what's at the back over here is the mass of nucleus plus the mass of electron. So even though we are focusing on the nucleus itself, we are adding back the electron that is surrounding it. So the result of that addition will be the whole atom itself. So you can say that what we have after the minus sign here is actually the mass of atom. So this is also an equation that we can use when the question gives us the mass of atom. We can use this equation over here, okay, where we don't put in the mass of proton, instead we put in the mass of hydrogen atom. Okay, so when the question gives you the mass of nucleus, you should be using this equation over here. But when the question gives you the mass of atom instead of the mass of nucleus, you can calculate it either by finding the mass of nucleus first using this particular equation to find the mass of nucleus first, then you use this equation to find the binding energy or the mass defect, or you can immediately find the mass defect through this equation here instead. Okay, so we don't need to manipulate it to get back mass of nucleus, but instead we change the mass of proton to be the mass of hydrogen atom. So this equation here also allows us to determine the mass defect, and if you c square multiplied by c square, you are able to get the binding energy. So this equation is also usable if you want to determine the binding energy, or if you want to determine the mass defect, we can use what's in the bracket here. So there are many ways for us to determine mass defect or binding energy. You just need to be familiar with how we manipulate things from one equation to another. When we change protons, mass of protons to mass of hydrogen atom, we are changing it from mass of nucleus to mass of atom. Okay, in some situation, you can change the mass of atom to be mass of nucleus by removing the mass of electrons surrounding the atom. Okay, so I hope that you can take up a pencil and paper and pencil to try to manipulate these equations following this video, and from there get familiar with all the different forms and structure that we can have to determine the binding energy and also the mass defect. Okay, so in the next video, we are going to move on to talk about binding energy per nucleon and how does it relate to the stability of the nucleus itself.